opportunities for engineers to get started. Let's hear it.
Hi everyone, my name is Kuzmin. I'm a ZK circuit engineer, and today I want to talk about the practical applications of zero-knowledge proofs, and we will take a look at a particular example of zero-knowledge proof application. We will follow the thought process behind transforming an application that was not a zero-knowledge proof application initially into a ZKP-enabled one. So, before we start, how many engineers do we have here? Do we have anyone who's not an engineer, who's not a software engineer? And how many of you have used ZKPs in practice? Okay, then probably it's a great audience for this kind of talk. So, zero-knowledge proofs are those wonderful cryptographic protocols that allow one party to convince, that the first party is called the prover, to convince another party, that is a verifier, that the prover knows some statement and that statement holds true without revealing any additional information about that statement. What it means for us in practice as engineers, like what is a statement? The statement that we want to prove is a computational statement. So any statement that we want to prove, we gotta transform into a form of a computational statement. And what it means that we shouldn't disclose any additional information about the statement is that, well, the inputs for that computation, we can just hide them completely. But at the same time, the verifier will trust us that we actually know those inputs and the statement holds true and the computation was carried out correctly. How do we do that in practice? We gotta transform that statement, we gotta compile that statement into the form of two separate programs. One of those programs is a prover program, another is the verifier program. And later, the proving party should run the prover program by providing all the necessary inputs and generate a proof, so that the proof can be passed to the verifier, and the verifier can verify the proof by running the verifier program. And a proof here is just a cryptographic object. It can be represented as a JSON file, for example. As simple as that. So, when I was starting my journey into the ZK land, I faced a problem. What do I start it with? So I was thinking about what could be a good hello world kind of application in ZK. And when you search on the internet, for example, some explanations of how zero-knowledge proofs work, you could find something that is easy to understand, but it's totally impractical. Some examples like the game of Where's Waldo, or an example of Alibaba Cave. And when you see such examples, of course, you ask yourself, how is it possible to transform some statement into a form of Where's Waldo's or Alibaba Caves? It's impossible. On the other hand, there are a lot of practical applications these days, and maybe you have already used some ZK rollups or you're familiar with ZK EVM, but these are very, very difficult, so definitely not suitable for your first like a hello world kind of application. So a class of problems that is easy, relatively convenient to use with ZK is the incomplete information games, like, running out of battery. I'll probably need my charger, I'm sorry. So, the incomplete information games, similar to Mastermind or Battleship, yeah, it's there. No, it's right So, the game of my choice, an incomplete information game of my choice, was a Wordle game. So, Wordle went viral a couple of years ago. It's a rather simple game where the players are solving a puzzle. Every day they need to guess a word that is chosen for that day. It's a 5-letter word and they have just 6 attempts to guess it, but for each of their guesses they get a color-coded clue. And the color coding is the following. Yeah, colors are okay on this display. So, if the letter in the guess is present in the solution exactly in the same place, the color is green. If the letter is present in the solution but at a different position, the color is yellow. And if the letter is not present in the word at all, the color is black. Why the game went viral? It was thanks to its social aspect, where the players could just share their game results on social networks, so that everyone else could see that, yeah, that player actually solved the puzzle, but at the same time they cannot see how the player solved the puzzle. So the player is trying to prove that they solved the puzzle, but they don't reveal any. Well, they reveal only some information in the form of those color-coded clues, but they don't reveal the actual clues that they provided. So it seems to be a good case for ZK, because maybe since there is already an attempt to prove the game stats, maybe we can somehow enhance it by using zero-knowledge proofs. So the original game is quite unsophisticated. It was just JS code running entirely in user's browser, and the game results that the users were sharing were just plain text. So there was like a room for cheating. You could just edit your game results theoretically. So maybe we can use zero-knowledge proofs to somehow to mitigate that. As we said, in zero-knowledge proofs we're proving a computational statement. So let's think about how we could potentially transform the Wordle game into a computational statement. We'll probably need some kind of function that establishes the relation between our guess, if we're the player, the solution of the game, and the color-coded clue that we're presented with by the game. So this function will establish that relationship. And if we think about a desired architecture of our app, of our resulting app, then maybe it's a good idea to share a zero-knowledge proof with other players instead of just sharing those like plain text results that can be edited. So if we share the proof, then probably it will be reliable enough. So the naive approach to that would be to run the prover on the side of the player, so that the player is the one who is proving their game results to anyone who is interested in that. Maybe other players, they can verify those results. But the problem with it, as with many naive approaches, is that it will not work. And we will see why in just a moment, for a couple of reasons. So, if we take a closer look at the statement that we're proving here, we will see that some of the inputs to the statement are the ones that the player probably shouldn't know, at least in the beginning. Because, well, one of the inputs to the statement is the solution. So we cannot let the player know the solution. maybe in the end it's okay, right? So, for example, we can imagine, okay, we can let the player play the game, and after player beats the game, it's okay to let them know the solution just to generate the proof, right? But there is another problem. Since the player is the one who is running the prover on their side, they can just substitute the solution with anything and then use the same value as their guess and just cheat in such a way and pretend as if they beat the game right on the first attempt. So maybe in this case, the prover should be some independent third party. So we could run the prover somewhere else somehow, and then we can prove the game stats to others, but to the player as well. So the player themselves, they will have to ask the independent prover to give them the clue for their guess, and then the similar process will be used to verify the end results of the game. But so we kind of solved the problem with the player cheating, but now we have another problem. Can we trust the prover? Because the problem with the solution substitution or any input substitution stays the same. So if we have an independent prover, how do we trust that independent prover? Or if we reformulate the problem, so maybe there is a way to somehow fix the solution to make sure that it will not be substituted during when the prover runs the proving function. And it turns out that there is a very useful cryptographic tool for that purpose that is called commitment scheme, cryptographic commitment. It allows some party that knows some data to commit that data by hiding it in some way, and after it's hidden it can be publicly exposed. But later, at some moment, if the party who is verifying, if that party wants to make sure that the data is exactly what was committed, then there is a way to open, colloquially saying, open that commitment and to demonstrate that the data that was committed is actually the right data. And one of the simplest commitment schemes is hashing. So it's enough just to hash the data, and later when the interested party wants to check that this data was actually hashed, we can just provide the pre-image. But of course here we have to remember that we don't want to be susceptible to the rainbow attacks, and we gotta hash the data with some random salt added to it. Otherwise it would be possible to pre-generate the possible values and just to guess what hash is that, for which pre-image the hash is. And in case of Wordle, it would be totally possible because, as I said, originally the game was entirely running in browser. It was just JavaScript, and the list of all possible words was extracted from there a long time ago, so it would be possible just to pre-generate the hashes for all the words and perform a rainbow attack in such a way. So, with all that said, if we take a look at a potential resulting architecture for our app, we would probably run that independent prover inside some kind of backend server. So that server will host the prover. Also, it will pick the solution of the puzzle for each day, commit that solution using a commitment scheme, a hashing commitment scheme, and put it on chain. When some player wants to play the game, they provide the guess to the server and they get the clue in return, and they also get the proof that this clue actually corresponds to their guess. And anyone else who wants to later verify their results, they can also take the proof and run it inside a verifier. And here we can see that our verifier, for some reason, is also it also lives on blockchain, and we will learn in a moment. We will learn why. So, as we said, zero-knowledge proofs are cryptographic protocols, but it turns out that there are a lot of them, a lot of different kinds of those, a lot of particular implementations of those cryptographic protocols. One of the popular ones is ZK-SNARK, which stands for Zero-Knowledge Succinct Non-Interactive Argument of Knowledge, which is a very, very intimidating, long name. But what's important for us here is that it's, first of all, it's ZK, it's zero knowledge, and second, it's non-interactive, so that the prover can independently generate the proof and the verifier can later verify it. They don't have to stay online, they don't have to communicate in real time to do so. And the tools that exist today to generate, to create ZK-SNARKs that are good enough for our purpose are domain-specific language that is called CIRCOM, that is used to describe those computational statements that we are proving, and a library called snark.js that allows us to compile those CIRCOM statements into the form of a prover program and a verifier program. And nice thing about snark.js is that it allows us to compile that verifier in the form of a smart contract. Why is it good? Well, probably because when we need a verifier, we want to make sure that the verifier will be the same for everyone who's verifying. So if we put the verifier somewhere in the backend server, then we would once again question, is that server trustable? But if we put the verifier on chain in the form of a smart contract, we can be 100% sure that it works exactly as expected. So, now, as software engineers, we're probably interested in how do we actually write those, how do we describe those computational statements using CIRCOM. Let's take a look. Those statements in CIRCOM, or those programs in CIRCOM, they're called circuits. And at first glance, they look a lot like the computer programs that we're familiar with, but there are some peculiarities, some differences. Colloquially speaking, programs are dynamic, so there can be loops with unknown number of iterations, like while loops. We can jump out of the loops, so in general the control flow is not defined, is not firmly defined, and there can be branching statements, if statements, but in case of circuits, it works a little bit in a different way, because if we had a statement that is dynamic, colloquially speaking, then how could we prove it? The statement should be defined, firmly defined, so we cannot allow, unfortunately, we cannot allow some of the dynamic constructions, like we cannot allow dynamic component declaration or jumping out of the loops and such. The reason behind that is that ZK-SNARKs use polynomials under the hood to describe those computational statements. We will not go very deep into cryptography here, but polynomials turn out to be very, very convenient for this particular purpose, for this particular use case of zero-knowledge proofs. And if you think, for example, how could you present a simple OR statement inside the if statement? How could you present it in the form of a polynomial? Then you'd probably get something like this. It really doesn't look like an if statement, but it does the same thing as like a similar thing that an if statement does, inside which there is an OR logical operation. So what it leads to is that programs, or let's call them circuits in CIRCOM, they look a little bit more complicated than those programs that we're familiar with. So here, huh? Oh yeah, okay. Thank you. Control C. Okay, I think it's good enough. So something that we could do in just like one line of code inside a for loop in probably any modern programming language. In CIRCOM, unfortunately, we need to do in a couple more lines of code. Like here, we are using a special component just to check the equality. Like this fragment of the circuit is actually it actually establishes the relation between clue and between guess and solution in terms of the green squares in the clue. So in those places where the guess is equal solution, the letter of the guess is equal to the letter of the solution, we should have the green square, and it's just a simple equality check, but in CIRCOM it's a little bit more complicated. Because, again, because of the polynomials, because under the hood that equality check is certain algebraic operation. And the reason why circuits are called circuits is that all those algebraic operations that are performed over polynomials, they actually look like pretty much like the gates in electronic circuits. And if we think about circuits, the circuits, once the components are soldered onto the printed circuit board, they don't change, they stay the same. We cannot like dynamically switch circuits, they're already there. So it's pretty similar to what we have in CIRCOM. Now, we were talking about zero-knowledge proofs, so how do we actually prove? Like, where is the proving in the statement that we're writing, right? Without without the certain syntax that we're going to take a look here at, those circuits, they would just perform a bunch of computations that don't really like restrict anything, don't restrict the relations between inputs and outputs. So this triple equal sign there, it's called a constraint in CIRCOM. If we think about it from like software engineering perspective, it looks a little bit like an assertion in the code. So if we have an assertion in the code and the assertion doesn't hold true, then the program will just crash, right? So in CIRCOM, if the statements on each side of the triple equal sign, if they're not equal, those statements, then you will just not prove the entire statement that they're proving. So here, this piece of code is actually checking that the solution that the server has committed on chain is obtained in the correct way, that it's indeed a hash of the solution and the random salt, and the commitment is indeed equal to that hash. So that's how you establish those important relations, how do you impose constraints inside circum circuits. Then when we finally need to put it all together and use it in our app, in our architecture, so what we do is we just take the circum circuit and we compile it. In case of Snark.js, the results are a WebAssembly file of a prover that we can run in any JavaScript environment. Like in our case, we'll probably have a JavaScript server, and we'll put that WebAssembly file and run it inside our server. And the verifier is the smart contract, just a Solidity smart contract that we can deploy on any EVM compatible chain. The proof itself, as I said, it's a cryptographic object. It doesn't look particularly pretty. It's just it's a point on an elliptic curve. So we can pass that proof to the verifier. Maybe we can do it in the same way as in the original Wordle. You're posting just the colored grid, just the game stats, but here we can also post the proof itself, so anyone could copy the proof and verify it. And the resulting UX that I came up with looks something like this. There are two key differences between the original Wordle and the result. First of all, you can notice that you need to connect to blockchain to be able to use the app. And the second is that for every clue that you see on the screen, for every color-coded clue, you can see that the clue was actually verified. There is a zero-knowledge proof for every clue, and it was verified. So, the main takeaway is that zero-knowledge proofs themselves, they're great, but you have to apply them correctly. Like in this case, if there was no commitment scheme used in this application, then the proof would just basically perform some computations and tell us that, yeah, there exists some data that yields a certain result. Like it is possible to find a combination of solution and the guess that produces a certain kind of clue, but it wouldn't actually restrict that solution to be a real solution. So you gotta use the commitment scheme to be able to actually prove something about some real piece of data that exists in the real world. Of course, it was a rather simple example, and there are still some open issues here that this application does not solve, and I can call, the first one I can call something like a game replay, where after the player has played a game round, they learn the solution, and then they can just play another game round in, I don't know, for example, in another browser or using another account, and just beat that game on the first attempt. And the second issue is the proof replay. So since we're sharing a simple proof of game results, so we're basically saying that, yeah, we knew the guesses that produced these kind of clues, and those game results, they're not in any way tied to our identity. It means that anyone else can just copy those game results if they saw them on like social networks and present them as their own results. But those two things, they require some solutions that are a little bit outside of the topic of our talk. So for this simple, like, hello world kind of application, I decided not to deal with these. So the app is actually live, so if you want to try, if you want to check it out, you can play with it. It's deployed on testnet. You will need some testnet girly ether to be able to play it. That's it. Thank you for your attention, and I'll welcome your questions.
Thanks for sharing. So, any question? 还是有要用中文问的，应该很多人英文很好，可以帮我翻译。
Alright, I got a question. Thanks for the vision. And you mentioned about the problem not solved, right? What's like right now? What's the most impressive or the people who can end up apply ZK with the GameFi project or anything related to the game right now? Because this is the one, like things like one feature like game replay problem. But what's the milestone or the thing when related to the game right now?
Well, this project is not in active development anymore. It was an example because it's the original game. It's probably copyrighted, so I'm not planning to create a clone of Wordle that does something in a different way, and it's like a commercial app. So I'm not developing it actively. But if you're talking about like how we could potentially solve those problems, right? So can I reformulate your question in this way? Yeah. So how we could mitigate those? For the game replay, we would probably just need to create some kind of penalty for the player to play an extra game round. Like if we put, let's say we just put a price on playing one game round, right? For example, you gotta lock up 1 ETH, and then for every attempt that you make, we deduct a little bit of ether, but maybe in the end you can win some if you solve the puzzle correctly. This would discourage you from playing, just creating another wallet to play the game, right? When it's free. So maybe some kind of disincentivization to create a new account to play it. With the proof replay, there is an existing solution that is already used in many ZK applications that is called identity nullifier. When there is some identifier that is also constrained inside the proof, like that identifier is generated. In our case, it would be generated for every game round per player. So you get a random ID that identifies you yourself and the game round that you're playing. And after you have proven your stats, that ID should be invalidated in a certain way, but normally it means that in some smart contract there is just a mapping of those IDs to their status, and that ID will get an invalidated status, and anyone else will be able to check that. So they will, if someone else would try to take your proof and present it as their own proof, try to pretend that, yeah, it's me, I solved that, not that guy. But actually there will be that nullifier in that proof that you could just go to the smart contract and check that actually, oh, this proof has already been shown, someone has already played, and maybe even see the person who actually played, if the proof is establishing a relation between the account and the proof itself. Yeah.
Perfect. Thank you. And I still I just randomly think about because right now seems like there's no like a game for adopted like smart contract or something about like for example like poker, like
Oh, I see.
you know
Actually,
you can play like 15 games and they can be simple like adopted some rules and they can play like 15 years like that.
well, actually, there is a really advanced game that is using zero-knowledge proofs. If you haven't heard, I suggest you to check out Dark Forest. It's a space strategy game, yeah, where they're using zero-knowledge proofs in a very interesting way to hide the game map. So it's like a strategy game with the fog of war, and they generate the map, but they put it on chain. So they're also using cryptographic commitment, of course, because you cannot just openly put the game map on chain, because in that game the goal is to conquer different planets that are scattered across the universe, and if you knew the positions of all the planets, you would immediately just go there and conquer them before anyone else. But since they're using a cryptographic commitment, then the data is there on chain, but only the one who like knows where the planet is can actually prove it using the commitment, but no one else can see it. Thank you.
Any questions?
Okay, you mentioned that we can use our circum to generate the circuit and proof, right? And I know some engineers use C++ to generate circuit and proof. Can you compare them and which one you prefer, or the benefit or the weakness?
Well, there is currently a number of ways to describe ZK snarks, to use them in practice. And if you're talking about C++, I assume that it's some kind of custom solution. It's not a framework. So of course, like all of that we were talking about here, you could just write from scratch in any language. I'm not familiar with, in particular, with some solutions that are using C++, but for example, the Halo 2 proving scheme that is also used in Zcash, it is using Rust, so it looks like way more like a low-level like programming. So it's not a DSL, it's not a domain-specific language, it's just plain Rust. You're writing it in Rust. So in the case of C++, I assume that maybe there is someone who's like writing it from scratch in C++. But Circum is a domain-specific language, so it simplifies a lot of things, and it has the like necessary syntax that is that should be used in zero-knowledge proofs, in particular, like those constraints and other things. On the other hand, for example, with Halo 2 in Rust, you go as low as like describing those polynomials that are inside the ZK snarks, which requires a lot of cryptography knowledge. So Circum you could simply use as like someone who's still new to zero-knowledge proofs, but if you are using some lower level language, then you will have to probably know at least a little bit of the underlying cryptography of ZK snarks.
Okay, so thanks Alice for sharing.
Thank you.
And it's about time, so we will have a lunch. And it's about time, so we will have a lunch break until 12:45.